All right. Good morning, everybody. I'm going to be finishing up my notes on infiltration today. Tomorrow, we're actually going to do a virtual lab. I have no idea how that's going to work, but before we get there, we're going to be doing or talking about these three words: porosity, permeability, and capillarity. So, to start that off, I'm going back to the notes that I was going through yesterday, actually on Friday. So these are the notes on infiltration. And we were talking about all the factors that affect whether water will go into the ground or just run over the surface. So infiltration versus runoff. And we already took a look at slope and we took a look at saturation, but we did not get to the last bit of this. So I'm just going to quickly go through these things and then we'll talk about porosity, permeability, and capillarity. So vegetation. So if you have a surface that is completely vegetated, meaning there's lots of plants, trees, grass, that vegetated surface is breaking up the soil. If you think about all the plants, they're breaking into the soil, and the water can get into those areas that are broken up and infiltrate. And also, water just hangs out longer on the leaves of trees, and if it hangs out longer, it's going to have more time to infiltrate and less time to run off. If you have a barren surface, meaning that you have no plants, then there's a lot less infiltration and there's a lot more runoff. So if you strip the surface of any plants, cut down trees, cut down forest, that's called deforestation. And if you have deforestation happening, you obviously have less plants, therefore you have less infiltration, and you have a lot more runoff. And so what would that do if you had deforestation? Well, less infiltration means you're going to have a lot more hazards like landslides, soil erosion. All that surface stuff is going to be swept away by the runoff of the water going over land. So deforestation leads to other problems later on down the line. Now, you can have natural deforestation as well when you have a wildfire. During a wildfire, all the trees burn down, obviously, and there goes your infiltration rate. So you have a lot of runoff, and typically after you have a wildfire, like out in California, they often have landslides because the trees are gone, and that's not holding the soil together anymore. Okay, so that's vegetation. Now, that directly relates to human land use. So if you think about the way we use the land, if we pave surfaces, if we build buildings, then we have impenetrable surfaces where water can't get into the ground anymore. And so it just sits on the surface. And so you have a lot of flooding going on. Now, obviously, we need to control that flooding. Otherwise, we're going to have problems like this amusing sign here. So how do we control that? Well, we build drains, and in some places they actually plant trees to help control it, and rooftop gardens and things like that. And that takes the water off of the surface and directs it somewhere else. Okay. All right. We did this question a while back. We talked about this and the idea that urbanization leads to more problems where you have a lot more discharge into streams, you have a lot more flooding, you have less of a time for the water to get there. It just runs off the surface. The answer to this question was 3, and that's just a little bit of review there. Okay, so finally we get to porosity. And this is a vocab word that you're going to need to know about. You're going to need to know how to calculate this, and we're going to do this in our lab tomorrow. So you'll get more explanation about this tomorrow. But just basically, if you think about the word porosity, porosity is referring to pore space. So how much pore space is in the soil, is in between the grains in the soil. So it's referring to this open space here. And it's essentially just a percentage of this entire thing that is pore space. And naturally, if there's no water present, the pore space is filled with air. Okay? So we can calculate how much pore space there is. And we're going to do that tomorrow. Now, more pore space, more gaps, means a higher porosity. And there are various factors that are going to make it a higher or lower porosity. If you have rounded particles, which I'm going to show you a picture about later, then you have a greater porosity. If you have well packed, they're all stuck together, then you have less pore space, so a lower porosity. Now, if you have a lot of pore space, greater porosity means water can get through here really easily. So let's take a look at some pictures. Okay, for example, which soil here has a higher porosity. In other words, which one has more air gaps between them. And that's pretty obvious that this one, which is all sorted, right? These are all sand size. And this one's unsorted. And you can see there's silt and clay mixed in there. This would be deposited by a river. This would be deposited by a glacier. So which one's got a greater porosity? Obviously, this one right here. So let's take a look at this picture here. We have a loosely packed sediment, so they're not really close to each other. They're pretty far apart. And we have this one where they're all really, really tightly packed. So if you pack down the soil, that squeezes it together, that squeezes out the air gaps, and therefore there's a lower porosity here and a higher porosity here. Now, that's packing, that's sorting. What if they're just different sizes? Okay, so if you look at these three pictures here, this one's got really tiny sediment, this one's got a little bit bigger, and this one's got the biggest. Now, if we had perfectly shaped beads, they're all the same, they're all round, and we were to put them into a jar and fill them to the surface, the only difference here is the size of the sediment. And if the size of the sediment is just different, that's the only thing different, then porosity does not change. And that's really interesting. So basically, if you think about these three pictures, the gap here is really, really tiny, but there's a lot of them. The gaps over here are bigger, but there's not as many. And if you actually do the math, you'll see that despite the fact that you might say, oh, those are big pore spaces, there's not very many of them. There's a lot of them here, but they're tiny. And so it all evens out. It's kind of interesting. So that's a big takeaway. Porosity does not change if the size is the only thing changing. Okay? All right. Now, this calculation here we're going to look at in our lab, so I'm going to skip over that for now. So that's porosity. Porosity is referring to pore space. Okay. Permeability. Permeability is the ability, notice the word, to permeate through the soil. So how easy is it for water to get into the ground, for gravity to bring water down? Now, if they're really tightly packed together, obviously it's hard for water to get through. If it's loosely packed, then it's really easily getting through there. Also, bigger particles have bigger gaps between them, and therefore they have a higher permeability. Whereas smaller sediment, like silt and clay, there's not really large gaps here, and therefore water can't get through there, and therefore it does not permeate. So it's got a low permeability. And we're going to do that in lab as well. It's a really easy thing to demonstrate the difference between larger sediment or smaller sediment. Okay? Something like clay is actually almost to the point of being impermeable, just like a piece of rock. You can't get water through it. It's so tightly packed together. The sediment sizes in between, or the size in between the small sediment is really, really small. Okay, capillarity. This is something I will also demonstrate. Capillarity is like the opposite of permeability. So permeability going through and down because of gravity. Capillarity is actually the opposite way. Water moves up against gravity, up back towards the surface. And whatever is true for permeability is not true for capillarity. They're always opposites of each other. So this is actually related to some chemistry. Water is a sticky substance. It likes to stick to things. It's got a high surface tension. That's why when you have a bunch of water droplets, it actually makes droplets. They stick to each other, and they'll stick to any surface that they can come in contact with. Now, if there's a lot of surfaces to stick to, there's a lot of capillary action. And that's really the difference between, the school paper towel, which does absolutely nothing, and the quicker picker upper, nice fluffy bounty stuff that picks up everything. There's a lot of, it's really, really thick, that nice paper towel that's super expensive. And therefore it soaks up the liquid. It pulls it up because there's a lot of surfaces to stick to. Now, smaller grains like sand and silt, there's a lot more surfaces, so a lot more of them. More surface area means a very high capillarity. Okay? If there's not as many surfaces to stick to, then it's got a low capillarity. Okay. So, and capillary action is the idea of moving upward. These three tubes are all in a pan of water, And you can see that this one's got a pretty wide opening. It's like a big straw, like the kind you get at McDonald's. And this guy is like that coffee stirrer, it's like tiny little opening. Okay. Water climbs up this one on its own against gravity because it's sticking to the sides of the straw. It doesn't climb as high in this one because there's a big gap there. It's hard for the water to cling to each other and to make it up against gravity there. But water will stick and rise against gravity, and it will do it the best in a very small straw. Okay? All right, last question here. The diagrams represent two identical containers filled with non-porous uniform particles. So they're the same container, same type of particles. The containers represent models of two different sizes of soil. The only difference between these is the size of the sediment. Compared to the model containing larger particles, this guy, the model containing smaller particles has what? Now remember, big thing to remember here. If they're just different sizes, same shape, just different sizes, then the porosity is the same. So, any question that has porosity in it, or any answer that has porosity in it, can't be true because it's greater porosity, greater porosity, greater porosity. The porosity is the exact same. But there is a difference in the permeability. Water can't get through here as easily. It can get through here really easily. So the difference is the permeability. This has lower permeability, and this has a higher permeability. This has a greater capillarity action, so the water can climb up through these gaps, but it can't through this one. So the answer to this question was D. Okay, that's it. I'm going to stop there. And remember, tomorrow we are going to do a lab, and I'll probably ask some questions about this today.